No. She doesn't have as much of a personality anymore. I don't know. I don't know if you guys heard the same thing. Recording in progress. All right, guys. Any questions before we jump back in to reviewing chapter 6 before we get back into chapter 7? All right. I'm glad to see you guys came back. There's a few people missing. We'll see. We'll see if we have to send out a search party. So what I'm going to do, let me first show you where this was again. We're going to look at the sheet that we looked at the first part last time. Let me show you where it is in here. So it's down, let's see, chapter 7. No, Jeff. That's for today. Gather. Chapter 6. Even more normal distribution practice. And I believe we did the New Zealand stuff. But just to kind of review, we'll do the San Diego stuff. Okay. So you're also going to need your Z-score chart. All right, let me stop sharing here and I'll share this instead. Kapow. So this is the one we did before. I don't know if you guys remember about the Taupo district of Waikato in New Zealand and how cheap their stuff is. So let's do this. If there's no specific questions out there about anything, let me make sure before. Yes?
What is this called on modules?
Even more normal distribution practice.
Oh, there it is.
Okay. It's the last thing in the unit 6, right? So is everybody able to find this up on Canvas? This is the thing we were working on. We did the first one together. And I said to do the second one yourself if you wanted to. So we're just going to do the second part together. Let me actually get my, sorry, I have to close that so I can do, I can't have too many things going on. Let me pull up my Z-score stuff. Scheisse, where are your Z-scores? Oh, crap, I don't know. All right, I'll just pull it up this way. Oh, I have forgotten how to do anything. All right, there they are. Okay, good. Stay right there. Just in case we need those. Okay, let's do this. All right, so let's take a look at this. So this was true. I can't remember the last time I looked this up. I don't know if this is still true. But the last time I looked it up, the mean rent for a 3-bedroom apartment here was $29,2308. Standard deviation of 352.21. Rents are approximately normal. That's not true, but what the hell? I just said it just to make a problem out of it. Find the probability that a 3-bedroom apartment here would cost between $2,000 and $3,000 a month. Can you guys just take a minute, if you haven't already done this, draw the picture out for me, shading in the area related to the question. And I'll just sit here and wait. And I'll just do weird things with my hands. Why not? What goes right in the middle?
The mean.
Yes. Which is
2,923.08.
Yes, don't forget the 8 cents. I like it. All right, get in there. Pretend like that's what that says. And then I want to know the probability between 2,000 and 3,000 So I want this area here. Okay. I like it. I can't let this go. Hold on. That's a really pathetic 9. Your whole job is numbers, Jeff, and you can't make a number. Okay, there we go. So now what do I need to do to be able to find that area that would equal the probability?
Subtract 2000 from 2923.08 divided by 352.21. And then
Alright.
do the same thing for the 3000.
And the only thing there is I think you got the 2, you said them in the wrong order, but the quick way to answer my question is make z-scores out of them, right? But I appreciate your attention to detail that kicks ass. But I want to change 2000 and 3000 into z-scores because, of course, I've got a chart that has all the freaking answers on it, but I can only use it if I have a normal distribution and I have z-scores to look up, right? So I got a normal distribution, but I don't have z-scores to look up yet. So let me make some freaking z-scores. So like she said, I'll do x minus the mean divided by the standard deviation, whatever the hell that is. Sorry?
Where did the 2,923 come from? Oh, I'm sorry. I think I'm looking at the wrong thing.
You might be. This is the one that says even more normal distribution practice. It's the last one in the Unit 6 module, right? This is question number 2 because we already did question number 1.
Oh, I got it. I was looking at number 1.
Oh, shit. So we left New Zealand. We came back to San Diego. All right. Did anyone get that z-score yet? Anybody?
It's negative 2.62.
If and real quick, let me see. Hold on. Give me. You're all like, just do what you got to do, dude. You're the freaking teacher. We'll wait. All right. If you get an answer like 1991 for a z-score, does that make much sense? Should that happen a lot? Where does unusual start for a z-score? Does anyone remember how far you got to go to get to unusual?
2.
2 steps up and down, right? So this here is officially unusual, right? So what if I got a z-score of 7? What would come to your mind? What would you think if you got a z-score of 7?
Something's wrong.
More than likely. So if you get a z-score of 1991, that's holy shit, right? Do you understand what I'm saying? So what I'm trying to get you to really get, this happens in every single math course you take. You put something in the calculator wrong, you get a number that doesn't make sense, but you just circle it and move on. Just don't do that. So if you put this in the calculator without parentheses around the top, the calculator will do the division first before the subtraction. Do you understand? Because it knows order of operations. And if you just put it in there like this, well, it's going to do division first, isn't it? Because it knows, please excuse my dumbass son, or dear Aunt Sally, whichever one you like better, right? So you have to put parentheses. So I know several of you don't have a problem with that. I love it. Some of you guys still have a problem with that. Be careful. And if you do it the wrong way, you get 1991, which you should stop and say, wait a minute, that's insane. Okay. I think I've made my point, hopefully. So don't just go, well, that's what my calculator said. You got to think about it. You got to Got to understand it well enough to know when things are obviously wrong. When you've made a mistake. All right. Has somebody already done this while I went on my little rant there? This other z-score? I got to change 3,000 into a z-score now. Oh man, every time I take a break, my writing gets even worse. I'm sorry. No.
It's 0.22.
0.22. That sounds about right. Let's see what I get. I got 0.222. All right, good. All right, now what the hell do I do with that? Do I subtract these?
Find it on the chart.
Yeah, you never subtract z-scores. That's crazy talk, right? A z-score tells you where you are. So if you subtract z-scores, you are somewhere else. I really hope that makes sense what I just said. It doesn't make any sense to subtract z-scores ever. So if I look up negative, let's see, let's look up 0.22 first. What do I get when I look up 0.22 in my z-score chart? Let me see, hold on. Where's my z-score chart? I have no idea. Z-score chart.
0.5871.
Let's see, 0.5871. That sounds about right. 2, yes, 5871. Kick ass, right? 0.2, 2. 5871. Please somebody write that down. And then the other one was negative 262. Is that right? I forgot what my z-score was. Let me see. Yes, negative 262. And when you look up negative 2.62, we get
0.0044.
0.0044. I like it. So let's come back. Oh, somebody's chatting at me. I can't handle it. Oh, okay. You're answering my question. Thank you. Let me see. I have forgotten how to use technology. Here we go. Let's see. Okay. So this area was 5871. Is that right?
Yes, that's right.
Thank you. Everybody's like, don't tell him. And the other one was 0.0044. So how do I find the answer?
Subtract them.
Yes. So 5871 minus 0.0044. And I get 0.5827, I believe. I believe. All right. So there would be, you could say this a few different ways. You could say there's a 58.27% chance that a 3-bedroom will cost between $2,000 and $3,000 a month. You could say 58.27% of all the 3-bedroom apartments in San Diego cost between $2,000 and $3,000 a month. They both mean the same thing. Does anyone not understand what I just said? Because we know this. If 11% of the people in a room like licorice, then the probability that I pick somebody who likes licorice is 11%. So they both represent, so that 11% represents two different ideas. It represents the probability of it happening, and it represents the percentage of the things that are that. Okay, maybe. Why am I making a point out of saying that? I have no idea. It could relate to future questions you could get. I don't know.
Madness.
Huh?
That's madness.
Madness, I tell you. Yes. Is there a method to it? I don't know anymore. How the hell do I do this?
Would you use the formula x equals the mean plus the z-score and then times the standard deviation?
Eventually, yes. Do I know the mean? Yes. Do I know the standard deviation? Yes. Do I know the z-score for the problem?
Not yet.
Not yet. Exactly. I like it. So how the hell would this look if you drew it? I'm going to find out where the answer is to help me figure out what the answer is. Where would the 15th percentile rent be on this picture? Would it be to the right or the left of the mean?
The left,
Yes. Why?
because it's a lower percentage.
Yeah, it's only supposed to have 15% in there. So it's got to be less than the mean. Does everyone understand? You guys remember that? The percentile and how to find it on the picture?
So if it's lower than 50, it'll be to the left.
Totally. Because the middle is the 50th percentile, right? The middle cuts it exactly in half. So if I move up above it, it's going to have more than half below it. And if I move down below it, it's going to have less than half below it. I really want that just to make complete sense. So if I could figure out what this z-score is, I could plug it in the formula and get the answer. That sounds like a good thing. So how the hell do I find the z-score? I like it. Somebody's got the suggestion in the chat. What would you tell somebody if they did this? All right, let's see. Here's 0.15. There we go, 0.15. I get 5596. That's a bunch of numbers. That should make Jeff happy. What have I done wrong? Here's 0.15, right? That's 0.15. What do you want from me?
Wait, why are we finding this?
That's my question.
Oh,
If you have a problem with what I'm doing right now, that's a good sign. You should have a major problem with me looking at 0.15 and thinking that has anything to do with this problem. I really want you guys with me here. I'm asking you what's wrong with what I just did. Is this the right z-score chart to look at? What did we just figure out? Where is our answer supposed to be? Isn't it supposed to be down here?
It's supposed to be negative.
Yeah. So what am I doing wrong? I'm looking at 0.15 as if it's already a z-score. But isn't the whole point, I got to look the z-score up? What's 0.15? Is it a
The
z-score?
area.
It's a freaking area. And where are the areas? The areas are in the body of the chart. In the body of the chart. I go walking in my sleep. Sorry. So 0.15. Let me see if I can do this. Am I this nifty? Yes. Okay. The closest you can get to 0.15 looks like a history test related to Christopher Columbus. No? What's the closest you can get to 0.15?
1492.
Yeah, 1492. Right.
Columbus sailed the ocean blue.
Yeah, and he screwed up everything. That's all right. We apparently let him off the hook. I don't know. Negative 1.0. What is the z-score?
Negative 1.04.
Yeah, negative 1.04. So I don't know if you guys understand what that does. We found the z-score that has 15% roughly below it. So isn't that the 15th percentile z-score? Isn't that what that is?
Oh,
Because what does a percentile mean? Doesn't a percentile mean the percentage below that thing? And aren't these percentages below things? I really want you to understand how this is really, this chart actually is a percentile chart in a real sense, because it keeps telling me the percentage below a z-score. So that's negative 1.04 is the z-score I need for this problem. There's more chats happening. There we go. Somebody was ahead of me. Hold on, guys. Let me get back to this other thing. There we go. Now I know what to put in here. I put the mean 2923.08. It's actually going to be minus 1.04. So if I start at the mean, and I go down 1.04 of these, I will end up at the 15th percentile rent. So whatever the hell that is, I don't know. Let's see. 1, 2, 1, 2, 7, 14, 2909, 2908. No, wait. You forgot to add 352, Jeff. 2908 minus 352 is 2556. I don't know. Can somebody save me from myself? Anybody?
That's what I got.
Yeah.
All right, there we go. Okay. It's just the math boy doing his thing here. Let's see. So I'll make that a rent. Bam. So if somebody in San Diego is paying that for the 3-bedroom apartment, they are in the 15th percentile. They are paying more than just 15% of people. So that's a good place to be for San Diego. All right. So this is the same thing here. You guys do this real quick. I'll sit here and wait. So I get for the z-score, anybody got that? Anybody?
1.08.
Ruh-roh.
Mm,
I don't know how you got 1.08.
I got negative 3.76.
Yes. It's interesting. So you got 1600 minus 292308 divided by 352.21. That definitely should come out to be about 3 3/4 steps down. Which is off the chart, right?
Yes.
So you could either say 0.0001, or you could say the slightly more correct, about 0%. I'll take either one of those. Okay. Does all this feel familiar now again? Has it resurfaced in your brain, or are you sitting there right now going, did we ever do this?
I'm kind of lost.
Well, shit. All right. So I really, all right. What part of this are you lost on, Nikisha?
After you calculate the z-score, I know I got it all the way to that, but then I got the negative 3.76. Is that the number that I look at on the chart to find?
Totally. That's right.
Okay. Then
And when you, all right, good. You had me concerned. I thought you meant you were completely like 0 of it. All right. And when you try to look up negative 3.76, it's off the chart, right?
Yes.
And that's where you could either put 0.0001 or you could just put about 0% chance.
Okay. With the little squiggly.
Little squiggly, yeah. Because that means it isn't equal to 0, but it's close enough for most humans, right? Most humans. Okay. All right. All right. Now, any questions from that kind of problem? All right, let me turn off my Bryce Canyon background. Goodbye. So we're going to transition now back into chapter 7. And I don't know if you guys remember this. Do you guys remember talking about alternate universe Florida, where the ages were strangely distributed? No? Do you guys remember that at all? You know, like, dude, who are you again? Yes, somebody asked in the chat, those problems were just like 6.2. That's right. So let's do this. I'm not going to do the entire spiel again, but I'm going to hopefully do enough to jog your memory. But I had a situation where there were a bunch of people from 0 to 20 or something, and then a bunch of people from 40 to whatever. I can't remember exactly what the numbers were. So here's the mean. And this is if I took one person at a time and plotted their age. So I have a bunch of people that look to be about 10, and I don't know, my scale sucks, but too bad. And a bunch of people that look to be in the middle of those two. All right, does this at all jog your memory? So this was alternate universe Florida. I went around to individual people. I said, how old are you? And they told me, I'm 97. I'm like, all right, you're 97. I'm 2. Okay, you're 2. This is if I choose one person at a time. This is like chapter 6, except it's not normal. But chapter 6 is all about pick one thing, pick one person. But in statistics, I'm normally dealing with samples. And if I have a sample size greater than 30, so if I go down to this alternate universe Florida, and instead of asking how old are you, getting their age and putting it on the picture, I say, you 37 people. Let's make this 37. You 37 people. Figure out your average age. What is it? 29? Okay, and then I plot that. Right? I plot 29. And then I ask another group of 37 people. And the most likely thing to happen is I get a mixture of people from all over. So the most likely average to get is the actual average. So I end up with a picture that looks like this. Really bad, Jeff, but sorry. We'll all survive. So last time I kind of went through it in steps, but just to get to the heart of the point here, if I take, now I really want you to understand, what's that point right there mean? That is a group of 37 people, and that point is their average age. So if the actual average of everybody is 30, shouldn't the most likely average of any group I pick be 30? If the actual average of everybody is 30, and I take a random sample of 30 over 30 people, 37 people, shouldn't the most likely average I get be close to 30, if not 30? So that's what this says. Look, where's most of the people? Close to 30. Where are there very few people? Weigh the shit out here. How likely is it that I get 37 people that are all right there? Is that very likely to happen? No. Therefore, it's in an area that has a very small area. It's got a small area. Sorry, I used the word area twice. Too bad. Okay, maybe. So chapter, I really want you guys to get this. All right, let me do this. Oh, before I escape from this, the means are the same. the means are the same. And really quickly, if I found the average age in here by asking each of you your age and then finding the average, would it be different if I took 2 people at a time, found their average, and then averaged all of those? Do you think the average age would be different if instead of taking 1 person at a time, I took 2 people at a time? Do you think the average age would be different?
No.
No, because me doing that can't suddenly make you older or younger, right? Now let me group you like this, and all of a sudden you're like, holy shit, I'm a little baby. No, that's not gonna happen. I don't have that power. So of course it's not gonna change the average if I just take 2 of you at a time instead of 1 of you at a time. Who gives a shit? So of course the average stays the same. But what happens to the standard deviation? What would you say about this guy's standard deviation versus this guy's standard deviation? This guy's is how related to this guy? Let me call this one sigma x. Let me call this one sigma x bar. Ooh. Which one is smaller? You could do this. What does standard deviation tell you? By the way, I'm sorry. I don't know if you guys noticed. My eyeball's all blood red. Sorry, I got my shot. Yay, that was at the end of my spring break. It was an awesome way to round it out. Anyway, sorry. What does standard deviation tell? The average distance from the mean to the data points. That could be a question I ask you on like a final exam or something. I don't know. So I don't know if you want to make a note out of that. Standard deviation tells you the average distance from the mean to all the data points. So which one of these has a smaller standard deviation? The top one or the bottom one? Which one of them has fewer data points further away from its mean?
The bottom one?
Yeah. Doesn't this rush to the middle? Does it get very far away from its average, the data points? No, most of them are right here. What about this one? There ain't none of them in there. They're way the shit away from their mean. So this is less than this. The standard deviation gets smaller when I draw a picture representing sample means, because it should be much less likely that a group of people get their data further away from the average, right? If you, and again, I think I asked this last time, if you go out and randomly pick somebody and you get somebody who's 80 years old, are you gonna like freak out and start yelling and running around to people? I found somebody who's 80. Are you gonna do that? No. If you go out and you randomly pick 30 people and their average freaking age is 80, would that freak you out? Yes, it should.
It must be in a retirement home.
You start to wonder, where am I? What has happened, right? And if I randomly selected people by picking names out of phone books around the entire United States, and my average of my 30 people came out to be 80, I'm like, what have I done? What kind of weird superpower do I have? Hand me a list of names that I can tell you who's 80. I'm like, what a weird, useless superpower. What a great addition to the X-Men I would be. All right, sorry. I really want you guys to understand. So this picture demonstrates that it is more likely to get an individual further away than it is to get a group of people further away. All right. So now All right, this is enough of that, because this is just concept. This is concept, and it's going to drive you insane. I want to get more concrete. It's still concept, but it's more concrete concept. All right. I'm in a rare mood today. I think I've been saving a lot of silliness up. I don't know. So I've got another handout up on the canvas. I don't know if you guys can see it now. Can you guys see Canvas? Anybody?
Yeah.
Thank you. So if you go to Unit 7, I don't think I had this active before. I might have. This bad boy. Go ahead and pull him up. Let me open him up in a better way for me here. Let's see. There we go. Up, up, there he is. Such a colorful handout for me. So this, believe it or not, is a more concrete example of the weird shit I'm talking about with alternate universe Florida. So this is not a perfect example, and I don't care. It's a decent example. Oh man, I'm losing people. What happened? What have I done? So say you put the numbers 1, 2, 3, 4 in a hat. Shit, I've lost 3 people in the last 10 seconds. What happened? They're all offended about alternate universe Florida. I'm sorry. All right, anyway, too bad for them. Does everybody agree that the probability distribution of picking a number out of the hat should look like this? What's the probability I get the number 1? It'll be 1 out of 4, correct? Is everybody with me out there?
Yes.
Okay. Some people logged off and then some people just walked away. I don't know what just happened. Is something happening? Anyway, so this is what it would look like as a uniform distribution. It's uniform because they're all 25% across the way. You guys with me? Shit, now I lost somebody else. All right. Is this normal? Is this distribution normal?
Yes.
Uh-oh.
Oh, I mean, never mind.
What is
Is
a
it
normal distribution? Sorry?
Is it uniform?
It's uniform, exactly, which means it can't be normal because a uniform has a flat top to it. What does a normal curve look like?
Bell-shaped.
Bell-shaped. I like it. So this is obviously not normal, but it's not gross. So we start off with something that's relatively nice. Now, in alternate universe Florida, I started off with something that looked disgusting, but then I took a sample of 37 people, right? So I really want you guys, the math gets so disgusting so quick if you want to really analyze this very detailed. So I'm only taking samples of size 2, meaning I really want you to understand this. If I reach in and pick a number and then drop it back in and reach in and pick another number, what could I pick? Could I pick the number 1 twice? 1, 1, or could I get 1, 2, or 1, 3, or and see? So see what I've done? Here are all the possible samples of size 2. These are all the things. So what I didn't do up here, I didn't list all the 37 people I could pick, and then and then another group of 37 people I could pick, and then another group of 37 people I could pick, and then holy shit, that would be a lot, right? That would be a lot. So to do this more concrete problem, I have to make it a much smaller scale. So I've got a relatively small set of numbers to pick from, and I'm only going to pick samples of size 2. I really want you guys with me here. So up here in my table, what was my data? Where did I get my data points from? I got them from the 1, 2, 3, 4. I got them from each individual piece of paper, right? That has the number on it. Are you guys with me? Or anybody not with me? So I could have got, if I pick one paper, I can get the number 1, or I can get the number 2, and so on. In this table, I want my data to be all the sample means that are possible. So if I pick the number 1 and I drop it back in and pick it again, What's the mean of that sample? That's an easy one. What's the mean of 1 and 1?
1.
Holy shit. Real quick, what happened to my lines? What are you doing, you weird thing? I don't know what happened. Anyway, sorry. What's the sample? And so keep going. What's the sample mean here? 1 and 2.
1.5.
Craziness. And then 1 and 3.
2.
There's a nice pattern there, right? Let me draw this in because it won't draw. You guys follow what's happening? So I really want you to understand. This is like, this is when I talk to individuals. 25% say 1, 25% say 2, so forth. This is now, I'm talking to groups of 2 at a time. And I say, average yourselves. And they tell me they're average. These are now my data points in yellow. So if I keep going, you start to see the pattern pretty quickly, hopefully, right? No? Yes? Maybe?
Is this going to be on YouTube?
Yes.
Okay, good.
Sorry. Now listen, real quick. We are still in the conceptual stage. This is not a problem that you will see an example of that you have to do. Do you understand? This is still me just explaining the idea behind something. And you're all like, good Lord, Jeff, get to a freaking point. I'm trying. Just stay with me. Does everybody understand what's happening, what I'm writing here?
It's just a lot to write down because if you don't print it out, like it's a lot to copy down.
Oh, well, all right. You got to figure that out on your side. But what you can do, well, I don't know. I've just got this bad boy open and PDF lets me draw on it. You could do it that way. But I understand what you mean. But there's not much I can do about that. I'm sorry. I can't mail each of you a packet of handouts. It sucks. Okay, now. So look up here. I really want you to understand. So up here, why were they all the same height? Why did this picture look so boring? It's a uniform curve because the probability of each data point was the same. They're each 1 out of 4, right? But now, what's the most likely sample mean to get? Look at all the sample means, everything in yellow. That's my new data. What's the most likely one to get? Is it most likely to get 2 or 3?
2.5.
Yes, 2.5. Why is it the most likely one? Because it happens 4 times. So look here. How did I fill in these? Well, how many total data points do I have now? How many total data points do I have?
16.
16. So 4 out of 16 are 2.5. That's why there's a 0.25 right here. 4 out of 16 is 1 out of 4 is 25%. How do I figure out for 2 and 3? Well, they both happen how many times? 2 and 3.
3 times.
3 times each. So 3 out of 16 comes out to be 18.75%. And so forth, right? I just filled it in, just counted how many times they happened. What's the least likely thing to happen? 2 things would be 1 and 4, right? And those are kind of related to if you just pick 2 people at random, it's less likely to get 2 really old people, right? It would be more likely to get a mixture of young and old. Does that make sense? Did I just say it's impossible to get 2 old people? No, I said it's less likely. So these extreme values have a smaller probability. They have only a 6.25% chance happening. So in the hat are the numbers 1, 2, 3, 4. And when I pick one thing at a time, each possible outcome has an equal chance of happening. Is that cool to say? You guys all with me, right? 4 numbers in a hat. If I pick one thing, then it could be a 1, a 2, or 3, or 4 at a 25% chance each. Straight and forward. If I pick 2 papers, pick one paper out, drop it back in, pick another paper out, take the average. What's the most likely average to get? 2.5. And then I can see how the other ones, and look, when I draw this out as a histogram, right? Here's 1, 2, I'm sorry, 1, 2, 1, 1.5, 2, blah, 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 right? Draw this out, go to the correct height. By the way, my scale is consistent. It's just rounded too much. Does this look more normal now?
Yes.
Yes. No matter what your population starts off looking like. The larger the number of samples you take, the more normal it will become. This one only needed a sample of size 2 to look normal because this, while it's not normal, it is pretty. It is nice. It is very simple. It is a flat, uniform thing. It doesn't take much to kind of make that become more normal. All right, so a couple more things to point out here. Let's do this. Let me see. Let me see if you guys can recreate what I've got down here. If I took, how do I find the average? Well, let's do this. Let's do this here. So has everybody got these written down? These
No.
guys here? No? All right. Somebody's chatting at me too. I can't take it. Okay. 2.5. All right. So let's do this. Let's remember, this is going to be a nice review. Let me open up my calculator while I'm letting you guys finish copying this down. All right. So what I'm going to do is I want to put that data in the calculator. We're going to do this nice and quick. Oh, crappity doodah. Where are you? There you are. So in the calculator, stat edit. That's all I remember how the hell to do this. Right. Let me see. Where did I put my? There we go. So I'm going to put in list 1. I'm going to go ahead and put the data 1, 1.5, and so forth. You guys with me? Because I want to know what this thing's mean is and what this thing's standard deviation is. No, John. All right, let's see, where am I? All right. Man, I keep losing people. What is happening? There we go. They keep, okay, they're coming back in. So if I put that data in, this is the data from picking 2 things at a time, and I calculate one variable statistics. So there's the mean is 2.5, and there's the standard deviation is 0.791. Why am I using a population? Because I did every possible sample, right? So it's the population of all possible samples. I know that might sound troubling. I don't know if you guys are with me. Did I take every possible sample of size 2? Yes. So that is the population of all possible samples of size 2. All right, so you guys see this? The standard deviation is 0.791 and the mean is 2.5, right? All right, I love you guys. I love you guys. Stay with me now. You're all like, you lost me about 10 minutes ago. Damn. All right, now watch. If I put the original information in 1, 2, 3, 4. That was the original data, right? On each paper, there's 1, 2, 3, 4. That was the original thing I was working with. And I do its one variable stats. I get 2.5. The mean is the same. Like I said earlier, the mean stays the same. It doesn't matter if you do it 1 at a time or 2 at a time or whatever. You can't suddenly make them all higher or lower. The average has to stay the same. Please let that make sense. The standard deviation, however, is bigger, isn't it? It's 1.29. I'm sorry, 1.118. Start looking at the wrong one. Got to look at the signal.
Sorry if we're like way past this, but so if it's the same either way, like why do we put it in with like the 0.5s last time?
Wait a minute. If the means are the same? What do you mean?
The means aren't the same, but the X bar. Sorry, I don't remember what that means.
Yeah, what's X bar, anybody? What does this mean, X bar?
Oh, that's the mean, sorry.
What kind of mean?
Sample mean?
Sample mean, kick ass. All right, now come at me again with the question, I'm sorry.
Okay, if the sample mean is the same, why did we need to do it that way?
All right, listen. The means are the same. The mean of the individuals is the same as, now look at this symbol. Look at this weird little symbol. This is the mean of the sample means. I really want this, I really desperately want this to make more sense than I know it does. If I have if a group is 1, what do I mean by that? I'm not taking 2 at a time. I'm taking 1 at a time. So 1, 2, 3, 4. The mean of those is 2.5. If I take them 2 at a time, like we did here, the mean of all their little sample means is still 2.5. So that was the point from earlier. If I take 2 people at a time from a room and find the average that way, it should be the same as if I took 1 at a time to find the average. It can't be higher or lower. It's the same people. Okay, maybe.
I think, oh, I got it. I was thinking that that was like a function that we actually had to do.
No. All right.
Yeah.
It's an idea. It's a concept. We're almost there, everybody. The standard deviation of these guys, remember we just got that was 0.791. So here we finally get something concrete. I'm really sorry. I know. But I'm hoping it makes sense that if I take groups of things, it should be less likely for them to be far away from the average, because what's the most likely outcome when I take a group? The most likely outcome is the average. If I take a group of people, I should get a mixture of young and old. They should come out close to the actual average. It should be very unlikely to get only young people or only old people. So most likely thing will be the average. So the standard deviation becomes smaller, but now I'm trying to show you that there's an actual formula for what the new standard deviation is going to be. The original standard deviation up here was 1.118. When I put 1, 2, 3, 4 in, that's what I got. If I divide that by the square root of the sample size, I get what the new standard deviation is going to be. Thank the gods. Can you imagine if every single problem we had to go through all of this work? I really want you guys to understand that this table, if I took samples of size 3, do you guys even begin to understand how much bigger this table would get? And what am I talking about up here? Samples of size 37. Do you want to see that table? I don't want to see that table. I want to know, is there a quicker way to do this shit? What do I need to know about my sample means? What do I always want to know about any set of data? that I've got. I want to know the average and I want to know the standard deviation. All right, I love it. You guys, now listen. If you have tuned out, please tune back in for me. We're done talking about concept. Let me really make it nuts and bolts, and we'll do some examples of problems you're actually going to see. So come back to me. Okay, I can sense people out there going, all right, come back. Okay. So let me summarize what just happened. Some of you guys might not realize what just happened. Here's what happened. So if I'm given a population, if somebody tells me I've got a population where the mean is 10 and the standard deviation is 3, right? If I take a sample, I take all samples of size, it doesn't matter, 8. Right? So I have a population, the average is 10, standard deviation is 3. If I take all samples of size 8, and I get so I take a little sample of 8 and I get its sample mean, and I take another sample of 8 and I get its sample mean, and I take another sample of 8 and I get its sample mean. I just keep going till I'm done or I go insane. What will happen is the mean of all those sample means, the mean of all the sample means of all the groups is the same as what it was for the individuals. Of course it is. We talked about that earlier. I can't make some of them suddenly go higher or lower. The same damn data points. They're going to have the same average. But the standard deviation becomes the old standard deviation divided by the square root of n. This, okay, I really want, all right. This is how spread out individual data points are from the mean. Let me say this again. This is a symbol that represents how spread out individual data points are from the mean. This is the symbol representing how samples of size whatever, size 8 in this case, how they're spread out from their mean. And as we saw, it gets smaller. If I take a group, their average should be closer to the real average than any individual could be. It's fine for somebody to be 97 years old, but it'd be really strange if a group of 30 people had an average of 97 years old. Holy shit, that's really weird. Why? Because they should be closer to the average age of all people, right? We inherently understand this. So what would the new standard deviation be? It would be the old standard deviation for individuals divided by the square root of the sample size. Why did you make it 8? You could have made it 9, Jeff, and you could have been really nice to yourself, but it's too late for that shit. What is that going to be? I don't know. Can somebody help me out?
Wait, before we continue, I'm like so lost right now.
Okay.
So you took the mean of the sample mean, and that's 10.
The mean of all the sample means. So I take a group of 8 people, right? So this is a group of 8 people, and I get a sample mean of something. And then I take another group of 8 people, and I get a sample mean of something. You with me? And I just keep doing that. I take another group of 8 people, and I get a sample mean from them. And I keep doing that until I get all of them, all possible samples of size 8. Does that make sense so far?
Yes.
When I average all the sample means I got, it's the same as what it used to be.
Okay.
And that hopefully makes sense. Because I like to say to people, if I'm talking about ages, I can't suddenly make people older or younger just because I took them 2 or 8 at a time.
No,
The average age stays the same. The average of the data points stays the same, but the standard deviation has to get smaller. It's weird that it gets smaller exactly like this, but it does. And I don't know what the hell it is. I don't know.
to make
Yes.
it smaller, you have to do the beginning standard deviation divided by the new sample size.
And be careful, not the new sample, it's just the sample size, right? It's just
Okay, yeah.
sample size you're taking. All right, so let's do now this is still not a concrete example. Here is the example of a problem you will get, right? This is an example exactly like a problem you would get. So average age is 45 with standard deviation of 13. We take a sample of 51 people, find the probability that the sample mean, here I'll write it out in English. Find the probability that the sample mean is greater than 48. All right, so let's investigate this weird ass problem. Doesn't this sound a lot like a problem from chapter 6? And you're all like, dude, it's been a week, but think about it. Just like the problem we did with the rents a minute ago. They give me an average, they give me a standard deviation. They ask about probably it's greater or less than something. Doesn't that sound like a chapter 6 problem? Yes. The difference is right here. We have taken a sample, and what's the question asking about? The sample mean. Not if I take one person, what's the probability that that person is older than 48? But if I take a sample of 51 people, what's the probability that the sample mean of those people is more than 48? Okay. So here's the trigger. When the shit, let me say this again. When the shit, Jeff, do I do this funky ass little equation? When the shit do I do this weird shit, Jeff? Well, probably when you actually take a sample and when they ask you about the sample mean. Let me say this again. When a problem takes a sample and they ask a probability about the sample mean, you have to change this. Because again, I really want this to make, I do. What does this tell you? That's the spread of individual data points. So so this right here works for individual data points. What is the problem talking about? Is the problem talking about individuals?
No.
What is the problem talking about? $51 people, right? Isn't the problem asking about 51 people? Yes? So I cannot use, listen. Even if nothing else has made sense today, listen. I cannot use a standard deviation for individuals if the question is asking about a group. I have to create the standard deviation that works for a group of that size. What does this funky ass little equation do? It takes the standard deviation that works for individuals and changes it into one that works for groups of size n. That's what it does. So what will the new standard deviation be? So step 1, figure out what the new standard deviation will be. So what will that new standard deviation be? Sigma divided by square root of n, so 13 divided by what?
The square root of 51.
Yes, so because n is freaking 51, right? Did I take a sample of 51? I'm talking about a sample of 51 people. And then whatever the hell that is. Now watch. I'm gonna keep saying this kind of thing. What have I done there? I've really messed everything up. All right. Doing my weird little thing where I invaded your space. I'm sorry about that. I really just bear with me. Just humor me for a second. This information is how, I didn't say it was normal or anything. I don't care if it is, but it kind of tells me how individuals are situated, right? I have the mean is 45. I have the standard deviation is 13. It gives me an idea of how individual data points are situated. For this problem, I need the picture that tells me how groups of 51 are situated. They have the same mean, but their standard deviation is different. It's not the same as this original. This is the one that works for individuals. I need the one that works for groups of 51. And what do you guys get when you do this? 13 divided by the square root of 51. Does anyone have that?
I got 1.8204.
Okay, sounds about right.
So do we only have to go out 2 decimal places, not 4 or 3?
Well, if I go out 3, there you go. And the math says, whatever, dude, it's the same number, right?
Okay.
So you have to go out at least 3. So if you want to go out 4 places, that's acceptable, right? Okay, I like it. Now watch, now everybody watch. Here's the part where the more comfortable you are with chapter 6, the easier chapter 7 is. How much work have I done so far for this problem? Very little, right? You agree with me? Most of it has been me just talking shit about trying to explain stuff, right? The actual work was this. Ooh, nothing. Now, how do I know this thing? Did I say this is normal anywhere? I know I kind of drew it as normal, but did I say it was normal anywhere?
No.
How do I know it is normal? This question, how do I know it's related to a normal curve? Who was listening earlier? Because n is greater than, does anyone remember? This is huge. This is how I know I can use the z-score chart. This is what tells me it's normal enough to use the chart of all the answers, right? If I just do 2, it does get more normal, but maybe not normal enough. If I use more than 30 and 51 is bigger than 30, then I know that it becomes normal enough. So how do I do this problem? Well, I do it the same way as always. Here's the mean. I'm curious about greater than 48. I shade that in, right? Greater than 48. I got to make a z-score out of 48. It's just that when I go to divide by the standard deviation, I don't use 13 because this is representative of a group of 51. What do I divide by? That one. That's it. I mean, I some of you guys are, I don't know, some of you guys, if you get angry, it's understandable that you're like, you put me through all that shit and that's all that happens. And I'm like, yes, I'm sorry. Yes. On the other hand, you should be thankful that that's all that happens. The only difference between a chapter 7 problem and a chapter 6 problem is the first step, and most problems are going to be change the standard deviation. All the rest of the steps are the same. I still do x minus the mean divided by the new standard deviation, whatever the hell that is. You know, I mean, that would be 1.63. I don't know. Somebody save me from myself.
1.648.
Oh, I suck. So 1.65. Right, so how do I get the area? What do I do now?
Look it up in the Z-chart.
Look it up in the Z-score chart, and that's gonna give me this area, and then I gotta do 1 minus to get that. I mean, do you guys, it falls right back into chapter 6.
Can you do the part with the square root and the division again?
Which, I'm sorry, this,
Yeah, right there. Yeah.
all right, so you take the old standard deviation
Okay.
divided by the square root of the sample size to get the new standard deviation.
Okay.
And I say new, and I really mean
That's the
standard
group.
deviation of the sample means, but you can see why I want to have a quick way to talk about it, right? I don't want to have to always say standard deviation of the sample means. So
Yeah.
I just call it the new standard deviation.
Thank you.
You're welcome. So that standard deviation would work if the question had been, if we take one person, what's the probability their age is greater than, then I would have, that's a chapter 6 problem. There's no reason to change this because this works for individuals. But the minute the question is about more than one person, oh shit, I need the spread that works for that size sample, not just one person. So of course I can't use this weird dude. I've got to make my other weird dude, right? So what do you get when you look up 1.65?
0.9505.
That sounds about right. So then our answer is going to be 1 minus that. So just under 5% chance. All right, so let's do this. Let's do this. Let me see. I'm trying to figure out if I want to do. No, let's do it. Let's jump to the handout. Not surprisingly, I have a handout, a worksheet, whatever you want to call this, a piece of paper with a problem on it related to this. Okay. I love you guys so much. I've traumatized you trying to explain the concept. And now you all probably can't believe that all that concept did was add one tiny little step. That's all it did, right? You know, like, damn it, Jeff, if you were a little bit worse of a teacher, you could have just said, do this shit, and then, yay, we wouldn't have to sit through your whole Florida bullshit. Oh, I'm sorry. I'll try to suck more better later. So let me see. If you go into Canvas under Unit 7, there's one handout there. You can't go wrong. Or maybe there's, oh shit, let me make sure I'm talking about the right thing. Have I unlocked it? Yeah, there is only one, and it's not the right one. Good job, Jeff. All right, everybody, hold on. No, I didn't want to do that. How do I get out of here? Here we go. I forgot how to use anything. All right, there it is. Let me activate it. There. Now, if you go to Canvas, you'll see two things under Chapter 7, Unit 7. Let me show you. Oh, I have no idea. If I lost anybody, if anybody checked out, went somewhere else, come back. We're gonna do something specific. All right. So if you look under Unit 7, Clt Practice. So what Clt stands for is Central Limit Theorem. And that's what we just did. So real quick, before we do this, what does the Central Limit Theorem say? All right, you ready? It says several things. It says, if you take a sample, then the average of all the sample means is the same as the original average, right? That's one thing it says. Second thing it says is the standard deviation of the sample means is equal to the original standard deviation divided by the square root of n, right? The new formula. You all with me? So it states what happens to the mean, nothing, it stays the same. Standard deviation gets smaller. Exactly by dividing by square root of n. And the third thing it says is, if n is greater than 30, the resultant distribution will be normal enough, no matter what it looked like to begin with. Let me say that again. If n is greater than 30, the new sampling distribution of all the sample means will be normal enough. Which means what? Which means I can use my sheet of answers, right? So since we know so much shit about normal curves, it's a huge thing in statistics to say, when will I know something's normal enough? Because if it is normal enough, I know all the stuff about normal curves. So in this case, if n is greater than 30, it's normal enough. All right, now, so has everybody found this? It's all about mineral density, which of course I know it's a topic that most college students are curious about. Bone mineral density, you guys found that? All right, now, so let me pull this up a different way so I can write on it easier. Where are you? There you are, okay. Oh, and just to really get you guys excited, this will be the last thing we do today, okay? Okay, this is a lot to come back from break to, I know. All right, here we go. I like doing this kind of problem. My mouse is dead. What has happened to you, little dude? You don't want to do anything. What has happened to you? Oh, that's exciting. All right, hold on, everybody. Why would that be true? Hold on, everybody. Oh, what has happened? Oh, I see what's happened. There we go. All right, all right, all right. There we go. Man, I tell you what. All right, no jokes about how old I am dealing with technology. Just keep it to yourself. All right.
It's unfair because you've had it longer than we have.
What's that?
Technology.
Oh, I don't know, dude. I don't know if it's fair or not fair. I just can't use it well. All right, here we go. So everybody read through this. It doesn't matter if you're not a bone mineral density expert. That doesn't matter. They give me an average. Don't worry about the units that much, right? And a standard deviation. And they tell me that they are normally distributed already. So I really want you to understand 1A, question 1A is a chapter 6 question. Why am I not doing this on 1A? Why is this not a part of 1A? Why do I not have to do that on 1A?
Because it just says a woman.
Yes, I'm not taking a whole sample of women. I'm just taking one woman. In fact, if I did use this, if n is 1, doesn't the standard deviation just stay the same? So, I mean, technically, we're always using that formula, right? Just for a sample of 1, it just stays the same. Well, that's neat, Jeff. All right. So, do 1A real quick. 1A is just a chapter 6 problem. Draw it, put the mean in the middle, put the number you're interested in, make it a z-score, blah, blah, blah. I'll sit here and wait. Maybe I'll start drawing too. Here we go. Oh, where'd it go? There it is.
Do we subtract the z-score from 1 on this one?
You mean the area? Be really careful.
Oh, yeah, sorry. Yeah, the area.
Yes, because when you look it up, you'll find this. As always, you find the area below.
Okay,
Since it wants more than, yeah, I like it.
thank you.
Sure. So like 0.32 or something. What'd you guys get for that z-score?
0.32.
No way. All right. All right. Like we said just a minute ago, if you look that up, you'll find the area below, and then you'll have to subtract that from 1 to find the other side, right? That's good old stuff. That's good old stuff. Old shit. Stuff we've done before. I have lost my z-score charts. I love it. Donde está? There you are. Okay. So what do you guys get when you look up 0.32?
0.6255.
6255, I like it. So you get 0.6255 down there. So what percentage of women have a bone density above 3?
37.45.
Yeah, 37.45%. You can make it a percentage if you want to. I love it. Bam! So the women with the strong ass bones, 37.45% have a greater than 3 gram per square centimeter bone mineral density. All right. You guys with me? So is that unusual if you found a woman that had bone mineral density of 3 or more than 3? Would that freak you out? No, it's 37.45. It's better than 1 in 3. It's not that unusual, right? It's not unusual. No, stop. So obviously I'm saying that for a reason. Now, a couple things in part B. Is N bigger than 30 in part B?
No.
Why does that not matter? Didn't we just do a number? Did we just do part A where N was 1 and nobody batted an eye, right? Anybody? Why does it not need to be bigger than 30? It started off already what? From the beginning, this thing was normally distributed. Do I need to pick a big enough sample to make it become normal? No, it's already normal. I want you guys to be with me on this. So when does the N greater than 30 kick in? That is if I don't know the original distribution, right? If I don't know what it originally looked like, I need N to be greater than 30 to be guaranteed that it becomes normal enough. I really want this to make sense. But if it already is normal, I don't give a shit what the sample size is. It could even be 1, like in part A, it was 1, and we did it because it's already normal. Okay, so part B, what's the very first thing I should do in part B?
Get the new standard deviation.
Hell yeah, this freaky ass standard deviation up here only works for 1 woman, and in part B, I got 22 women, right? I need help. I need the right spread. I need the spread that works for groups of 22. I can't use 0.31 because that works for 1 person, right? So I'll take the old standard deviation, the 0.31, divided by what? I'm sorry, I think you just said it, but I can't remember.
Square root of 32.
22.
Oh, sorry.
That's right. And then whatever the hell that is. 0.0693. I have no idea.
It's
get-
0.066.
Oh, I was off. Sorry. I apologize. Sounds about right, right? Is that what you guys get? Oh, shit and a half. What have I done to you, calculator? Calculator. Yeah, 066. Oh, no, yeah, 11. Okay. So everybody with me? You guys all right out there? And then what do? I really want this to make sense. I know I put you through hell. I know I did. I know I did, but I had to. I had to explain why this makes sense. And now that is the only new thing in chapter 7. This is the new thing in chapter 7. What do? Do you see how it's the same question basically, but it's about a sample mean now? So the picture is going to look the same. It technically would be a little skinnier, but who gives a shit if we're just drawing a picture for myself? But when I go to make a z-score, I'm not going to divide it by 0.31. I'm sorry. I'm going to divide it by 0.066. So do you guys understand? It's the same exact work. I just have to use the correct spread. That's all chapter 7 ends up doing. I'm really curious. I'm kind of curious if anybody out there is like, then why the shit did you take us through all this shit when that's all that happens? I'm sorry.
You made it seem more scarier than it had to be.
I did. I'm sorry. I'm sorry. I'm very sorry. That's why I desperately tried to tell you. Didn't I tell you, you will never have to do this? Didn't I say that a few times? I try to. All right. But I don't want you to not, I need you to have a connection to why this makes sense. Why does it make sense that the formula makes the standard deviation become smaller? I'm hoping after our discussions that makes more sense. Okay. So I don't know. What do you guys, let me see what I get. Don't say anything yet. I get 1.5 basically. So 1.51.
Would it be rounded to 1.52 though, because it's 1.5151?
I want you to understand, I just did it in my head. So if you want me to get more precise, no, you're good. You're good. So it is 1.52. I got pretty close, but you're right. It's 1.52.
I thought that was like your final answer. I was like, wait, did I do something wrong?
No, I appreciate that you think I could be that precise in my head, but I can't. But anyway, sorry. You're fine. You're fine. And now I just look it up like I did before, right? Look up 1.52. That'll be this side. So what do you guys get when you look up 1.52?
0.8461.
0.8461. That sounds about right. So go ahead and double check if you haven't looked it up yet. So then what's the answer here?
I got 0.9357.
Ooh, interesting. Let's take a look.
That's what I saw.
So did
Yeah. All right. So who gave me the original answer? Can you double check? So 1.52. Here, let me look it up too. Bum, 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 bum. Yeah, 9357. Thank you.
Oh, I went one too far down.
Understood. What was it again? 9357?
Yes.
Thank you. So 0643. Does that look better? So 6.43% chance. So I really want you to understand what I've just done with this problem. To get one woman with a bone density of more than 3, that is a 37.45% chance. I would not be surprised to find one woman that has a bone density more than 3. To find 22 randomly selected women and have their bone density, their average bone density be more than 3, that's only a 6.43% chance of that happening, right? That is certainly freakier. That is certainly less likely. Are you guys with me? And again, don't lose sight of the fact that if I take a group of people, whatever I'm taking the average of should be close to the actual average of the population they came from. I mean, I really want this to make sense. Again, if I just randomly took from the entire United States, I just randomly took 30 people, and their average height came out to be 7 foot, am I not going to go, what the hell just happened? Right? But if I randomly picked one person and their height was 7 foot, that would be a little freaky, but I'm like, all right, they exist. What the hell? But 30 people and their average height is 7 foot tall? Holy shit. That is so unlikely. I'm sorry. I'm saying shit. And there's little people out there. All right. You know what happens on this show. So sorry. I'll try to be better. It ain't gonna happen though, but you know, I'll try. All right. Do you guys feel better now? I'm sorry. I do have to go through the explanation. Now look at number 2. Number 2 is interesting. I really doubt, was anyone here? I don't think anyone here was born in 2004. Right? That would put you at 17. I guess it's possible. I don't know if I have a 17-year-old in the class. But if somebody was born in 2004 in California, their life expectancy was 80.2 years. Isn't that crazy? No? You guys are like, whatever. With a standard deviation of 14.9 years. And I give you some links. Look at me being all good. I give you the links to verify that what I'm saying is correct. So part A, I love this question. Hint, hint. I love this question. Hint, hint. If we select a sample of 37 California infants, and I should say born in 2004, why is it okay to use the z-score chart to find the probabilities?
Because
There's
n
more
is
than
above
30,
30.
so normal distribution.
There we go. N is greater than 30, normal enough. Can anyone tell me what says that?
The sample?
No. So says the what? Anybody remember what this was?
Oh.
So says the central limit theorem, otherwise known as the CLT, otherwise known as chicken, lettuce, tomato. So if I say chicken, lettuce, tomato, I mean the central limit theorem. That's the dude that says if n is greater than 30, it's normal enough. And it says the mean stays the same and the standard deviation changes. All right. So you guys do part B. What time is it? All right, we're doing okay. Just to make sure everybody starts this off right, what's the very first thing you should do?
I'm going to use standard deviation.
And what is it exactly that tells you to do that?
The sample.
Yeah, I took a sample and I ask a question about the sample mean. Those are your triggers. Those are what tell you to do this right here. Okay, I like it. Keep going. Dadgummit pen. Oops. What are you doing? Stop doing weird shit. All right. Oh, this is interesting. So, did you guys get this? For the standard deviation?
Yes.
So if you want to round that to 3 decimal places, it should go to 450, right? People always freak out when there's a 9, but it just says take this up to 50 instead of 49. That's all. Or don't round at all, right? It's up to you. This one's nice because the area matches with what the table's going to tell me. People get a little 1- happy. They start doing 1- to everything. It's like, no, come on. So does this match with what you guys are doing? Did you guys, you know me, I make mistakes. So when you look up -212, what do you get?
0.0170.
It's like 1.7% chance. Okay. I like it. I understand this question is a little morbid, saying if you got a group of 37 kids, was probably they'll die before they reach 75. It's a little more, but it's a low probability. It's only a 1.7% chance. So more than likely their average length of life will be more than that. Okay. I'll tell you what. All right. I don't give us any breaks ever. So I'm gonna end class right here, and we're gonna do these 2 next time. That'll be a nice review of what the hell we've done. Hopefully, and I know. I try to tell you that we were talking about concept, which is always a lot more difficult than the actual nuts and bolts. But the actual nuts and bolts of chapter 7 are very straightforward. You just have to be careful about sample sizes. And so if I give you a problem, like if this sample size had been 19, what would we have done? If instead of 37, I said 19, what would that mean?
It's not a normal distribution.
I like it. So what would I have done? Could I do part B?
No.
Exactly, because where did we get this number from? Holy crap, Jeff.
The chart,
Sorry?
the Z chart.
Z-chart, and that only works if I have a normal distribution. So if it's not normal enough, we cannot do anything. We just don't do it. If we had a stats 2 class, I could teach you something else to do, but we don't have a stats 2 class. So unfortunately for us in stats 1, if n is not bigger than 30, we could not answer a probability question because I can't use the chart of answers because it only works for normal curves. All right. Okay, otherwise that's enough. So let me know if you need to hang out afterwards, if you have any questions. Otherwise, you are free to go
Thank you.
anytime. Like all kinds of math to share.
Thank you.
You're welcome. All right, guys, I'll see y'all later. Oh, somebody's chatting me. Anytime.